If it asks you to simplify, then I'm looking really for kind of three things. I'm looking for you to factor. I'm looking for no negative exponents. And I'm looking for no complex fractions. So no like fractions divided by fractions. So if I'm asking you to simplify, then I'm looking for you to take care of those three things. You don't have to do any sort of fancy factoring. You just have to pull out anything that's sort of obviously common to both terms. Was that, again, like the last question, right? I head off on my own direction, but I think that hopefully covered what you are interested in.
Yes, yes,
Okay.
it is very clear. Yes, thank you.
Okay, good. I mean, with all these rules, they're hard to see sometimes, right? It's like there's a lot of parts, but once you see how the parts like fit together, then the rules are very, very cut and dry, right? There's no, you don't really have to do a lot of thinking here if you see this in the right way, right? You know what A is and you know what U is, and you just follow the formula and it tells you what the derivative is. Of course, the challenge is to see, you know, this combo in the right way. And that comes a little bit from experience. Hopefully you've gotten that experience now, and just some kind of good understanding of those rules, those basic rules. So this would be another one I would expect you to probably write down on your review sheet. You won't see tons of those, but I would certainly expect that to pop up at least once, if not twice, somewhere. Now, if, like I said, if for some reason you didn't write it down on your sheet and you slipped on the ice and hit your head and couldn't remember it, you could still do pretty well even on a problem like this by just showing me this format, and then you would just sort of have to leave part of it blank and say, I can't remember the derivative to this type of function, right? And I'd say, well, okay, you should have known that, but you got the rest of it, so that's good, right? And in some ways, that's almost a smaller part, right? You can always look that up at some later date. But if you can't see the structure of the problem, that's a more sort of a more consequential error. Okay, other questions?
Yeah, I had a question.
Great.
But it's on the review test part 2.
Yeah, that's fine. Let's see if I can get that up. Give me a second, I'm just pulling it up here. Review test part 2, yes. Which number?
4C.
4C. Yes, okay. So this is xy cubed plus 5 equals the square root of y. And you are trying to find dy dx, which is just the derivative of this function. Now, you are expected, or I hope that you can see that this is an implicit function, right? It is not like our previous function where we have y equals in terms of x. Here I have x's and y's mixed up together. So that's telling you it's an implicit function, even though I'm not actually telling you that, right? That's part of the problem, is to recognize that. So when I look at this implicit function, I see 3 different terms. The 5, of course, being the easiest because the derivative of 5 is 0. And I need to take the derivative of all of those pieces, right? Implicitly. So the implicit derivative means anytime I take the derivative of y, I'm treating that as some function of x, and I have to use the chain rule. So for this one, the derivative of the square root of y would be 1 over 2 square roots, right? That's the derivative of a square root function. I evaluate it at y, and then I multiply by the derivative of y. You could write the derivative y prime if you like, or you could write it dy dx, since that's what I'm looking for. And the derivative of 5 is 0. Here, the derivative of x times y cubed, this is a product rule. Very common error, people forget to use the product rule. It's really just like this, kinda, right? Like it's some function times some other function, right? This is x, that's one function, and y cubed is some other function. So the product rule says the derivative of x times y cubed plus x times the derivative of y cubed. The derivative of y cubed is 3y squared. And again, I multiply by dy dx because of the chain rule, right? Like if I were taking the derivative of the sine of x cubed, the derivative would be 3 sine of x squared times the derivative of sine, which would be cosine of x, right? So sine is my y, cosine of x is my dy dx. And that's exactly what I'm writing here. I just don't know what y is, so I don't know what dy dx is either, right? That's the whole question here. Whenever you do a derivative implicitly, after you've taken the derivative, hopefully properly, then there's just some algebra to rearrange it. So when I look at what I've gotten here, I have 3 terms. I want to move all the terms with dy dx to one side. So that I can factor the dy dx out of those terms. It looks a little messy, but I'm not doing very much, right? I'm just keeping track of all the other parts as I pull the dy dx out, and then I divide. And I get y cubed over 1 over 2 square roots of y minus 3 x y squared. Sorry. Now, I will say when you're doing these implicit functions, I am not worried about simplifying the answer. I want you to solve for dy dx, but we don't need to worry about simplifying here. This is a complex fraction, so that would be a form I wouldn't like in general, but I wouldn't mark you off on this problem. If you did need to get rid of that 2 square roots of y on the bottom, you could multiply both top and bottom by 2 square roots of y. You'd end up with 2. This is 3, and this is 1/2, so that's 7/2. The 2 square roots of y would cancel there, and you get 1 minus 6 y to the 5/2 times x. I ran out of room. Got a little messy. But that's not actually necessary here, right? This answer is just fine for implicit differentiation. Questions about that? Did that help?
Yeah, that helped. Thank you.
Okay, great. Other questions?
I would like a review on the last problem of part 2, which would be the cubes and identifying like the rate of change of the heights and widths and so on.
The cube, yep. Do you want to just work through that or talk through that one?
Yeah, just walk through it. Just I want to see if my logic is correct.
Yeah. Here, let me let's try. Oops, sorry, I missed the question. Yeah, that example, that's a 3 that was sin x to the third. So handwriting, always an issue. All right, I have this one pulled up. So, I feel like I'm not sharing the right thing. Okay. Okay. Can you guys see that problem? Is that?
Yep.
Okay. So we have this rectangular solid that has a square base. The length of each side of the base is growing at 4 centimeters per second, and the volume is growing at 60 cubic centimeters. How fast is the height changing when the lengths of the sides are 10 centimeters and the height is 6 centimeters? Show your work. Yikes, right? Like when you read that the first time, it feels maybe overwhelming. But we just want to start by breaking it down, right? So this is a related rates question, and I want to start by defining the variables carefully. Luckily here, they're already defined for me, right? I already have the X and the Y written, right? And it is indicating here that I have a square base, so both the sides there are X. And so if we're starting this problem, I like to kind of start with the rates that I know. I know those rates are going to be important to me. And so, right, the volume is growing at 60 cubic centimeters per second. That's this, right? That's how I express that. And the length of each side of the base is 4 centimeters per second. So that's dx dt. How fast is the height changing? So I called that y. So I want to know dy dt. With these related rates problems, knowing that those are the rates that I'm interested in, I want an equation that connects those 3 quantities. And with geometric examples like this one, basically always, well, I don't know, I hate to say always, but very often, right, it's our geometric formula that connects the things I'm interested to. You know, some problems that have triangles in them, sometimes people introduce like a sine or a cosine, but I would only want to do that if the angles were something I cared about, right? If it's just the lengths, then I don't want to introduce some other thing that I don't care about, right? I don't care about the surface area of this this rectangular solid, so I don't want to bring that into my equation at all. Yeah, good question on the geometric formulas. I won't be you shouldn't have to write anything down. I expect you know the volume of a rectangular solid, but if it was like a cone or something, I would give that to you on the exam. So I guess you should know like basic 2D shapes and rectangles and things, but anything beyond that, I don't expect you to know those offhand. Okay, so once I have this formula, now I need to take the derivative of it implicitly. So the steps here are very important. If you jump ahead a step, you have a really good chance of getting off track. So I want to define my variables, then I come up with my formula, then I take the derivative of that formula, and I have to remember that all these things that are changing are variables, and so I need to treat them that way in my implicit differentiation. So the derivative of volume is dv dt. And when I take the derivative of x squared y, that is a product. Both x and y are functions of t in this scenario. So the derivative of x squared is 2x dx dt times y. And the derivative of y is, of course, dy dt times x squared. So it is an implicit differentiation, but x is not the variable here like it was in our last problem, right? In the last problem, when I took the derivative of x, I just got 1. But here with the application problem, x is a function of time. Everything I'm taking the derivative of is connected to time. Once you have this, you should be mostly home free, right? This is a formula. I just need to plug in all of the missing values and I'll get what I'm interested in, which is the dy dt. Okay. I know dv dt. It tells me the sides are 10, so I know x. I know dx dt is 4, and I know y, the height is 6. And I just plug those values in, multiply it all out, and then solve for dy dt. It does, in this case, give me a negative. How fast is the height changing? It's actually shrinking, which maybe seems counterintuitive. The box is growing and the sides are growing, but the volume, I guess, is growing so fast, or the sides are growing so much faster than the volume's growing, that in order to keep the volume, you have to actually sort of be slowly shrinking the top. And again, some of that is just these results are not always intuitive. That's the numbers here are hard to square in your head, right? The sides are growing at 4 centimeters per second. The volume's growing at 60 cubic centimeters per second. I don't have a good sense of what that means, right? And that's, I think, probably part of the reason that we end up with this negative growth or shrinking of the height. Was that helpful with that, or?
It made sense.
Okay. So, and then, you know, you won't see exactly the same problem, obviously, but you can work through those exact same steps. So what and that's what I'll be looking for when I grade these. Did you define the variables and write them out using this notation, dx dt, dA dt? Did you come up with the right equation that sort of connects them together? And then did you take the derivative of that equation implicitly? And then did you try and solve it? Now you can certainly make mistakes at any one of those junctures, right? You could pick the wrong variables or pick the wrong equation or mess up some of the values when you solve it. But if you can show me that you're doing the process correctly, you're still going to get a lot of the points, most of the points probably, even if you make a small error. Okay. Other questions?
I have another question about like sketching the derivative. It's a
Yes.
simple question. So on number 10 in the first review, there's just like the small like quadratic at like the bottom, and because I knew like I could kind of estimate what the quadratic would look like, it was easy to find the derivative and like graph it. But if you got like a graph, you had no idea what the original equation is, how would you sketch the derivative of it?
Yeah, good question. So let's take a look at that one. Okay. So sketch the graph of the derivative of the following function and indicate where the function is not differentiable. So it's not, first of all, it's not differentiable at any sharp corners or discontinuities. So if you have a sharp corner or a discontinuity, it's not going to be differentiable. And so you need to indicate those like I did here. You also should, you know, for your graph, it will be helpful to remember those not differentiable points are potential breaks in the graph and jumps in the graph of the derivative. They don't have to be a break or a jump, but you kind of want to like restart your graph on each side of those not differentiable points. Okay, so that will be helpful for you. So when I graph this one, you know, all I was thinking here is, well, okay, this is a line, this first part, and this line then has a constant slope, and I can measure that slope at 1, right, over 1 and up 1. So that's where this portion of the derivative comes in, right? That derivative is equal to that slope at every point. Okay, and then I start over because it's not differentiable at this sharp corner, and I look at this. This is another line. This actually has a slope of, I would say, -3, right? So I'd say my scale here is not great, right? It's down here at -1. I probably should, not probably, right? But I should have drawn it down there. I'm not going to be too picky about that for you, as long as you're close. You know, with a line, we can get the exact slope. So I'd say you I probably should have done better on that one. But certainly with the curves, it's unclear always what that exact slope is. So your question was like, okay, well, how would I do this parabola? Your thought was, well, I know this is a parabola, so maybe you're thinking of it as a derivative of a parabola, but you actually don't even know. I mean, it could be part of a sine curve or some other weird function that we don't know. So it's not, just from the graph, it's not really clear exactly what this derivative should look like. All I can really tell you is that for the x values over here, the slopes are all negative, and they're getting closer and closer to 0, right? Because the slope right there is 0. So I know this point, and if you had drawn your graph looking like this, I'd say that's just as good, right? That's also expressing what's happening with this parabolic-like portion of the graph. Okay. So again, what I would be looking for here, the main things would be that you found where the slope was 0, and you have where the slopes are positive and where the slopes are negative correct. The magnitude, like whether it's up here or down here, when you have a curved graph, I'm not going to be that interested in. Okay. And then finally, this third portion, again, I kind of start over. That's 1/2. This graph looks more nicely positioned right at 1/2. But all of these with the graphs, we're just estimating. So I know there was like on one of the group works, some of the graphs, you know, it was like, people were saying, well, it's like, looks like it's about 1.8. That's fine. I mean, but don't stress out about trying to get it estimated exactly. As long as you're close, you're going to be fine with those when you're reading it off of the graph. And I know as a student, it's hard to know like what part matters and what part doesn't, right? So it is probably best just to be accurate, but if it's close to a whole number, you feel free to estimate it as that whole number. Did that answer?
Yes.
Okay, yeah, it's a good question, and I think lots of people will be helpful to many of you, I think, to have seen that and gone over that a little bit more, how we estimate that. So it's just, and if you get some weird function that's sort of messing with your head for whatever reason, just go ahead and pick a couple points on it, estimate the value of the slope, and plot those points. And then you can just connect those, and that's going to be a good graph of what your derivative is. Okay. Other questions? anything else? Okay. Yeah, those were good, I think, really good questions to start with. I guess the one other topic that maybe, you know, going back to the first part of the course, you will have to evaluate some limits. Don't get those mixed up with derivatives, right? The derivative involves a limit, but there's also just straight up limits, right? Just the limit of some function. So I give you the limit as x goes to 2 from the right of e to the x over x squared minus 4. It's not a derivative. It's just the limit. What's happening to this function as x goes to 2 from the right? And so your strategy should always be to plug in that value of x and see what the top and bottom are heading towards, right? So in this case, the bottom x squared minus 4 is going to 0, and the top is going to e squared, which is like, you know, close to 9. So from that, you should be able then to decide what strategy you want to approach the limit with, right? If the top and bottom are 0, then you're going to try and use algebra to rewrite that. If in this case, like in this case, the top is not 0 and the bottom is 0, you're going to make a note and say, okay, this I know is going to be infinite. And then the question is it positive or negative? So I go back and I notice here that e squared is certainly a positive value. Since x is going to 2 from the right, their value is bigger than 2. So that's going to make x squared bigger than 4. So that's going to be plus. Right? And so I know then that that's plus infinity. So you know, just remember that this has nothing to do really with derivatives. It's not. It's just a limit. But we'll see and have to work a little bit with that as well. So that sometimes the new idea of derivatives kind of wipes out some of the old ideas that we did, and I don't want that to happen. So just kind of keep in your mind straight what is a limit and what is a derivative. They're connected, but they're definitely not the same. Okay, so otherwise, I think you guys touched on the other couple things that I wanted to make sure to talk about. So I think it's a good review. Again, make sure just right after class, go ahead and fill out the time that you're interested in for taking that midterm. And if something does come up with your schedule where you need to change it, just send me an email. I will probably schedule the emails to go out tomorrow. So if something comes up like tomorrow night, don't just go in and change the quiz at that point. I'll have already scheduled everything. You'll have to send me an email, and then we can try and sort something out if there has to be some adjustments. Yeah, I think that's all I have. Make sure you have that review sheet. You're welcome to use a scientific calculator. No graphing calculators or graphing tools are allowed or really shouldn't be needed. And then make sure that you are showing your work, right? You're showing your thinking. It is a test, so you have a somewhat limited time. So you don't need to show me every single step or write out, complete sentences. Just a note or two or some symbols that indicate what's going on, like this example. That's plenty of information to tell me how you're thinking, and that's what I'm looking for. You can't just do this. right? Like if I say, what's the limit? And you say plus infinity, you're not going to get full points for that because I don't know. Did you just guess and get lucky, or who knows? So you got to give me a little information about how you're coming up with these answers. Again, there are some that are really simple or straightforward. There's nothing to show. But anything else where you're doing some thinking, you got to show me a little bit of that thinking. Okay, so with that, I will let you go. If you had any other questions, you can ask me, and certainly, you know, if something comes up, you can email and talk to me later too. I agree, those were good questions. Those of you that asked, I think everyone benefits from those good questions. So keep that up, and yeah, good luck. Good luck studying and getting ready.